Hello everyone, my name is Immanuel Echeverri. Today I will present you my poster titled Extracting, Describing, and Representing Spatial Features of a Chemical Reaction inside a Virtual Reality Learning Environment. This work has three sections. First, its pedagogical framework. Second, how this pedagogical framework was built upon a virtual reality environment and its development. And finally, the preliminary results from this pilot study. It is important to highlight how elapsed time was used as a weight factor to improve and to provide a measuring scale for our qualitative codes, and more on that later. And at this point, I'm asking you, the viewer, to choose your own adventure. For time convenience, you can choose one of three options. You can either see the video in its entirety, or skip to the timestamps shown below to jump into a section that you're interested in. So here begins the pedagogical framework section. Let's begin by talking about the chemistry. We chose this reaction because it is a visually demanding reaction where many things happen at the same time. First of all, two bonds are formed. Second, 4 carbons change their geometry. And finally, 8 atoms change their position in space. Molecules' orientation and direction of approach affect the outcome of the reaction, producing substances with atoms placed at different positions in space. This highly visual reaction provides an excellent opportunity for a virtual reality visualization tool, as we can provide an immersive 3D environment for students to observe these changes. As you can see in the video, we are highlighting the 4 carbons that are changing geometry, and at the same time, we are showing the 2 chemical bonds that are being formed. And simultaneously, we're showing the 8 elements that are changing their position in space. Everything is smoothly shown in one simple animation. So there are 3 theoretical frameworks taken into consideration. First of all, from the visual perception field, we use findings from the literature, meaning optimizing salient features and 2D object orientations to design a scaffolding in the form of a familiar, recognizable shape that can be used as a reference to pinpoint positions of elements in relation to each other and the molecule as a whole. The content is delivered using the cognitive apprenticeship model, which is perfect for the virtual reality environment due to its student-centered nature and one-to-one interaction between content and learner. Interactivity attributes were taken into consideration to produce affordances that are expected from any virtual reality experience. The results of blending these 3 frameworks was a hexagonal prism reference frame in which a Diels-Alder transition state can be mapped. The shape is then used as a tool to extract, describe, and represent spatial features in reference to this familiar shape. Our hypothesis is that visual spatial skills can be improved from 4 fronts, which are perceiving dominant features, observing groups' relative positions, enhancing 3D representation, and identifying stimuli despite variations. These 4 fronts can be improved using our virtual reality learning environment in the future. So this concludes the pedagogical background section. Continue watching for the technical aspects of the virtual reality environment, or skip to the timestamp below to look for the preliminary results. So here I'm showing you the result of the scaffolding and how this allows for observing the spatial positions of elements in relation to each other and in relation to the molecule. So, regarding the workflow for the development of the virtual reality learning environment. To promote accuracy in the representation of molecules and their behavior, we decided to use computational chemistry calculations as the source of all our molecules and animations. As there was no program available to reliably import these calculations into a 3D modeling software such as Blender, we extended the Blender Python API with our own program, which is currently submitted to publication. Long story short, this program reads the Cartesian coordinates of the atoms from the calculation output and creates a molecule using primitive objects in Blender. For the animation, each of the frames obtained from the calculations were converted into a 3D object. All of the objects were imported to Unity, where we used the animation utility class to create an animation from the position and rotation of each child in each frame and assign it to one game object. The animation can be then accessed both using the animator component or as a legacy animation. So this slide is for any other student beginning to use the XR interaction toolkit. After reading its documentation, I initially used the try get feature value method for some Boolean operations to listen for user input and subscribe to them. I created some custom classes which were needed, and each had its own update loop. This was actually painfully slow. Then, less than a month ago, I discovered an asset that allowed me to bind input into actions, which then can be referenced in the inspector. This made the development faster and hopefully way more efficient. Another problem encountered with the XR interaction toolkit was that the XR rig objects only hold one controller at a time. It was necessary to use a class to manage which controllers activate for which type of actions. Here, there's a lot to discuss and there's a lot to learn on my part, and I would appreciate any type of comments or emails that you can send. So regarding the pilot study, we gathered 10 first-year chemistry graduate students as volunteers to test the alpha version of the VRLE. Due to COVID-19 guidelines, the interviews were done remotely. The students were isolated inside an office where an Oculus Quest was placed on top of a chair and inside a tape square where the Oculus Guardian was already set up. A screencast from the headset to the computer was arranged beforehand, and the headset had its sensor blocked with tape so that the students could drop right into the experience. Once the students arrived, they were asked to share their screen via Zoom video conference, which was then recorded. No latency issues were experienced. This, in my opinion, is the heart of the data analysis section. The Zoom video recordings were uploaded to YouTube as unlisted videos, where we use the platform's native subtitle system to process the transcripts and obtain not only conversation snippets, but also timing information down to the milliseconds. Note that each of the snippets end where there is a silence. This was used as a non-biased way to assign elapsed time to each coded incident extracted from the conversation snippets. The subtitle file was uploaded to Excel, where it was refined and later analyzed. So here are some of the VRLE video snippets that I would like to share. There are some QR codes for you to look for more videos in the time that you have. And I would like to show only one of them here. In this rotation task, the student is asked to grab an atom from the 2D representation in the 3D model. Once they grab the correct element, the object reverts to its initial position and changes its rotation randomly. And then the student is asked to grab a different element. Immediate feedback is received from the interaction. That way the student can check whether or not the action has been done correctly. This shows the preliminary results of the pilot study. Herein, I'm showing raw data. It is still uncertain whether the information collected can be used to back a claim with any level of confidence. The value of the data is the way in which it was obtained. As to the best of my knowledge, elapsed time as a quantitative way value for qualitative codes is a new approach. Today, we will focus on one student who was the slowest to answer most of the questions, highlighted here, and had to leave the interview after the 10th question due to time constraints. We chose this student as the variety of tools they used to analyze and answer the questions was, in my opinion, interesting. As the student used several different approaches to solve things, here, the elapsed time becomes a useful tool to discriminate between the tools the student preferred to use the most. So I would like to define technical difficulties in this graph. So technical difficulties arise when the instructor's guidance is not being understood by the student, when the student has no idea how to continue, or when the instructor is struggling to give clear and concise instructions. We added the elapsed time in which all of these instances occurred, and that is shown here in this graph. These students spent the majority of their time in the modeling stage of the traditional cognitive apprenticeship model and experienced very few technical difficulties, as they had previous experience with VR environments. It is hypothesized that this previous experience allowed the student to take the most from the experience and thus solve most of the questions with ease. This claim will be tested once all the data is analyzed. From this section, it is interesting to highlight that the student used all the representational systems to refer to molecules and chemical processes, as well as different heuristic strategies to facilitate their decision-making throughout the questionnaire. The visual spatial skills that was used the most was visual orientation, which stands for perception of positions of objects in space in relation to each other and the observer, meaning that the students used this orientation and mental rotation of objects to pinpoint the position of all elements very often. So more information regarding the visual spatial abilities, representational systems, heuristic principles, spatial challenges, and other things will be disclosed after the analysis of all the interviews is completed. The findings of this pilot study are being used to develop a more student-centered iteration of the VRLE, in which the guidance of the instructor is not needed. The technical difficulties usually encountered in these pilot studies are being taken into consideration for the environment's improvement. And here is an example of an improvement of the human-computer interaction that we are currently developing for the drawing system, which was one of the parts that required the most improvement after the pilot testing. Thank you for your attention. If you don't want to see the videos with more details, make sure to go to the video links. This concludes the presentation. Have a wonderful day.